Hello everyone. Today I'm going to share with you what I learned regarding the hybrid scheme to simulate the jagged reality of the rough Bergomi models. So let's ground ourselves with the empirical reality. In standard models like Heston, we pretend the volatility moves in a nice smooth waves like this, uh, which is purely a mathematical convenience. But real volatility is rough, jagged, and unpredictable. This roughness is governed by the parameter called alpha. As it moves away from zero and gets closer to minus 0.5, the path becomes increasingly rough and non-Markovian, which is the true empirical reality of the market. Because it's so jagged, the standard simulation methods fundamentally cannot handle it. So, how do we mathematically model this roughness? We use the Volterra integral. Don't let this view intimidate you. We will break it down. Uh, think of this function as the deterministic kernel, like a memory weight. It dictates how much a random Brownian noise shock from the past impacts today's volatility. But there is a catch. Um, the rough um, in the rough models, this memory kernel takes the form of power law, so x to the power of alpha. Um, because the roughness is negative as time s approaches the present moment t, the value of the kernel rockets immediately to infinity. This memory blow up is the core mathematical challenge we have to solve. Which makes sense because, like, as we approach the present, we theoretically give importance to the like one or two steps before the present, infinite weight. So normally to simulate the paths, we chop them into small flat steps, uh, like the standard Riemann sum. But we look at what happens when we apply the flat rectangular steps into our rough memory kernel, because the kernel spikes to infinity near the present moment zero. Drawing flat boxes completely misses this massive spike. This leaves a huge chunk of missed area, shared shaded here in the red, which represents massive approximation error. As a result, the standard Riemann sum gives you volatility paths that are artificially smooth or mathematically broken at extreme roughness limits. So, to fix this missed spike, we introduce the hybrid scheme architecture. The core idea is simple. If the spike breaks the model, we isolate the spike. We divide it into two distinct zones. Zone 1 is the recent past, so the immediate one or two time steps closest to the present where the memory spike actually happens. And zone 2 is the distant path. We will use a different math approach for each zone. For the first zone, um, we to resolve the singularity of V in the recent past, we completely abandoned the flat rectangular steps. So instead, what we do, we use the exact calculus. So we keep the true mathematical power function and calculate the exact analytical integration against the driving Brownian motion. As the implementation node points out, you do not need to do this for the whole timeline, capturing just the immediate one or two time steps, like so k is 1 or 2. Mathematically, sufficient to resolve this singularity error. So for the second zone, there are no spikes, so you can safely use the first simple flat step approximation using standard Brownian increments. But we will use a smart tweak inside the optimization box. So instead of just picking the start or the end of the time step to draw our flat box, we calculate a mathematical optimal evaluation point inside the step called B star. As you can see here in this chart, choosing the specific optimal point over standard forward point actively minimizes the MSE, keeping it flat at 0. So now we have the slight simulation challenge. We have two different types of noise. We have our exact continuous integrals from the recent past and our discrete Brownian increments from the distant past. To make them work together, we combine them by sampling from a joint multivariate Gaussian distribution, finding the exact correlation matrix between these two different types of random noise requires calculating their exact overlap. To mathematically correlate them, we use the tool called Gauss hypergeometric function, denoted as 2f1. Now we have the flawless math framework, but if we try to do this for like thousands of historical paths, the computation gets incredibly slow and tangled at the cost of n squared. The brilliant optimization is noticing that the distant path is structured as discrete convolution, and because it is essentially a matrix of kernel memory weights over a matrix of random noise. By passing this convolution pipeline through a fast Fourier transformer engine, we drastically accelerate the simulation and having a cost of n log of n. So if we put this into action, the first step is to simulate the rough Volterra core process using the fast hybrid scheme we just built, and then we plug this into the exponential function to generate our spot variance, and we use the spot variance to derive the actual stock price ST using the standard Euler discretization driven by the correlated Brownian motion. Our goal is we reached it, can now easily compute like, European call option using the Monte Carlo simulation. And let's just see a conclusion. To conclude, the rough volatility where alpha is less than 0 introduces an extreme mathematical singularity that causes massive approximation errors in standard simulation. So the solution, we use the hybrid scheme, which divides it into two zones. It applies the exact precision to recent past spikes and optimized approximation of the far tail, and then combining them and using fast models like the FFT convolution. This hybrid scheme achieves exact simulation accuracy to produce perfect implied volatility smile without sacrificing any operational performance.